We go on with the next presenter, and at the end we have the discussions. I want to invite Christoph Lubbers. He is a consultant from Haskoning. He will tell us something about asset control of wastewater mains, and then the technology, what can technology do with it. Christoph is also a researcher, or ex-researcher, or he graduated at the University of Delft for his doctoral thesis. And I give you the floor.
Yeah. Thank you, Luc. My speech is about asset control. It also has to do with information that we use from the system. Asset control can be seen as a part of asset management, which is a container word, but asset control is looking at performance rather than all the different different parts of a system. I think that by using asset control you can improve wastewater transport system performance. So outline of the speech is first on the introduction. It's about wastewater pipelines and what we do there, and the problem we have with these transport systems. To illustrate what we are talking about, there's a case study we did, a troubleshooting project, where we use this information to solve the problems. I tell something about the methodology we have used, and then back to the analysis of that case study, the results we had, and yes, it's better. And of course I conclude with discussion and conclusions. So what are we talking about in the Netherlands? If you talk about wastewater, the municipalities collect all the wastewater that drains down to a low point where the pumping stations are, and that's transported by pipelines to the wastewater treatment plant, and that's one of the tasks of the water board. So they transport and clean the wastewater. The problem here is that these transport systems are poorly equipped. So we're lucky if there's a flow meter that tells you what the flow is, but there's no information about whether the pipeline is has a large resistance, or it's clogged, or something happened to it. We don't know whether pumps are working at the right performance. We only know, if we're lucky, what the flow rate is. So if you have to work around these transport systems, we make non-informed decisions. And when you do that, you spend money that's not necessary, you use manpower that's not necessary. And last year there was a commission that calculated these inefficiencies, and they say we can spend or save 380 million euros per year in the wastewater sector. Okay, problem description. If you design these transport systems, they're normally based on clean water. We know that there can be sediment in it, solids and gas, but we are not really taking that into account. And because sewage is of course not clean water, you have all these aging processes. And if you talk about aging process, you talk about pump wear, because all the sand and dirt is wearing the impeller down, so the performance go down. You have clogging of the pumps. If you look at pipelines, you have sedimentation, biofouling, gas accumulations, and all those processes make sure that the performance will go down, and you want to check that. Another thing is that asset management is not advanced often at the water board, so they don't know really what kind of pipe there is, what age, which material. So if you don't know that, you cannot act quickly or act with focus on problems. So if this information of the system performance is not available, you don't know when you have to do your maintenance. You don't know if there's a trouble with your system, what you can do. Also, when you have to make policy about new investments or capacity increase, you do that based on theoretical approach and not on the real values. So back to the case study. This is a influent pumping station to a wastewater treatment plant. It was brand new. So on the left picture you see 4 pumps, and it's a very simple system. Water comes down to a reservoir. It's on the right side of the picture. It's somewhere here. So with a short suction pipe, it goes into the pump, up in the wastewater treatment plant, and then runs down. And what they saw when they commissioned the plant is that the flow rate, excuse me, right. Check. Okay. What you see here is the flow rate in time. So you see here, for example, a rainy period, a rain event. This is less rain. This is no rain. This is dry weather season or dry weather events. And what you see here is suddenly the flow rate will go up, and then the flow rate completely goes down and lower to a minimum flow rate that is normally there. So what you see here is not in the pictures, but that's the pump is working to its nominal speed, and the pump performance goes down completely. So this is what they were facing. So it's a brand new system, brand new pumps, nothing special, simple transportation system, and still it goes wrong. So the first issues the water board had was environmental, because the water is not going into the treatment plant, it's spilling somewhere in the receiving waters. So that's an environmental problem. But another problem was they didn't understand what happened. It was all new. Their advisor said nothing was wrong about it. So a lot of people were gathered around the problem, and they were speculating, working on gut feeling, do arbitrary decisions, and they had no clue when they would solve this problem. And the big problem was that they also had some additional money to spend, because they need temporary pump units to make sure that the pumps were that the water was going into the treatment plant. So they have to rent the pumps, which was expensive. It took over 9 months to solve this problem, and they spent a lot of manpower on that. So the methodology we used is what we call IWATT, and it stands for Intelligent Water Transport. And what it does, it makes use of the SCADA or the process data of the plant, so normal flow rates of the pumps, pressure, speed of the pumps. So normally you would get a graph like this, and based on that you don't know anything yet. It doesn't give you information, it's data. And what IWATT or IWATT does is it presents information that you need. So as an administrator you can say, I want to show the performance of a pump. I want to know where the duty points are. I want to know whether transportation system is, or the pipelines is corroding, or the resistance is going up. You want to know what happens. It gives you information when you do maintenance. You can make policy about that because you know exactly how it works. It gives you information. And also investment. Do I really need capacity increase or something? So if you want to know if a system is working okay, you have to refer it to the reference, which is normally the design. And I don't know whether these graphs are familiar to you, but this is the design operating range of a pumping station. So you have the pump curve at this nominal speed and the minimum speed, so the pump can operate in this section. There are lines for the system, so the minimum system pressure and the maximum system pressure. And you can tell the pump to work at the minimum flow and the maximum flow. So all the duty range is lying within these lines. So that's my reference. So what IWATT is telling me is giving me information. Where are those points then? So it's just a reference between what actually happens in practice and what it was built for to do. So here you can see that a lot of the points are within this gray section. There are also points that are outside of the section. So you can check into that. Another thing you can check is, and these the people that do the sewer studies are interested in this one. What you see here is the suction level at the pumping station, and you see the flow rate, and this blue line is the set value for the flow rate for a pumping station. So during dry water flow, the pump is just kicking in and kicking out along a certain line. And when it's raining, the water increases, the water level in the suction reservoir increases, and the pump is sped up to the new water level. So all the pumps, all the duty points should be lying on this blue line. So this is, say, a month worth of duty points. And what you can see is that when it really counts, when it's raining and the sewer system is completely full, these pumps are failing. So now you want to know, are these 1 million points in this 10 or 20? So what's the percentage of the time that the pumping station is failing? And what we do now is just to take these statistics. And that's shown here. You see the flow rate distribution of the flow rate distribution in percentage and the deviation of it. So if the pump would be working okay, all the points would be on the 0 point, and pump control is working fine. So what we show to the administrators of these pumping stations is, look, say 12% of the time it's working less than 25% of its set value. And this was pump 1. And if you look at pump 2, this one is not doing what it's supposed to do, but it's doing better. But still, it's not doing what it does. So based on the statistics, the administrators can pinpoint the problem pumping station and say, okay, these are the ones that we have to look and take care of. So back to our case study, the IWATT technology we're using for this problem. And it's the same what we're doing here. We didn't also know what the problem was. So this is a time series of the discharge. So these are the dry water events, dry water flow, and this is a stormwater event. So what we do is we check one of the pump cycles and we plot the duty points, and they should be all on the pump curve. So with dry weather flow, the problem is not there. But if you look at the stormwater flow, you see that the duty point starts at the pump, and then gradually, this is about 2 hours, the duty points come from the QH curves or the pump curve, which means that the pump itself is failing. So now we have to check what's the problem. During dry weather flow it's okay, and during stormwater flow there's a problem. So if you put that next to each other, you can try to combine the conditions and what the pump does. And during dry weather flow we say that the gas content in water is low. And if you look at stormwater flow, all the water is coming from the air when it rains, of course, and the gas content of air is high. During dry weather flow, the flow rate of the pump is low, and it's high for higher flows, which means that if this is the pipeline going to the pump, there's a certain lower pressure at the entrance of the impeller. And what you see is that during dry weather flow, this inlet pressure is high, and during rainwater flow, stormwater flow, it's high. Together with this high gas content, we believe that degassing might be a problem. So all the gas wants to be in the center. It's rotating, so gas goes to the center, water goes to the end, and that gas pocket is blocking the pump. So our assumption was you need a different impeller, different type of impeller. So the hypothesis was degassing at the entrance is a problem, might be a problem, and it has effect on this particular pump impeller that they choose. Okay. Solution was to change the type, and with one where the axis is not full, where the axis is full, I mean, so gas cannot concentrate itself in the middle. So we did that. The water board was convinced that because we had this information, that would be the problem. So they said, "You're right. Okay, let's do first the conclusion." The problem here was that because they lack information, that problem lingered on. They spent a lot of time and effort in it, but they didn't know what the problem was. And the moment you have the right information, you can focus on the direction of the solution. You know what it does, and what could be the cause of the problem. And because you have this support, the water board was willing to pay these expensive tests to change the pump. So the discussion, I think, is well, in the future we probably have less money to do more work, and everybody's saying we have to do the right things and do them right. And then if you want to do that, information is key. If you don't have the information, it's not working. You cannot act right. So what the board should focus more on gathering this information and disclosing them for their assets. So that asset control, paying attention to performance, what the previous speaker also was saying, that should be integrated in the risk and assessment and asset management policy of the water boards, I think. So the advantage is if you have the right information, for maintenance means that you can focus your maintenance on a condition-based approach. You're watching which pumping station is not working, and you pay attention to that. And for investment, it means you can really check whether the capacity is too small, and you can ask yourself whether a certain expansion of the infrastructure is really necessary. And also for policy, if you look at what in the Netherlands we call the OAS studies, that are quality studies for emission of a total water system, wastewater system, you can check whether the conditions that are used or the assumptions that are used are really accurate. So you don't pay attention to theory anymore, but you look at the real practical data that you have. So last slide, this is how in south of Holland a system could look like. It just gives you the red warning signs of a pumping station or a pressure line that doesn't work. And you can pay attention to that, and this could be a display at some central point in a wastewater treatment plant or something where the administrator can look on. So, any questions?
We're going to have the discussion afterwards.
Afterwards.
Yeah.